in the Zoom link or in the Zoom chat. And yeah, again, welcome everyone. Thank you, Soumya.
Thank you very much, Nadira. So next on the agenda is what we all have been waiting for, the keynote address of WiDS Sri Lanka Conference. So today we have with us Dr. Radheeka Jayasundera Abeyweera. She'll be speaking on causal inference for smarter decision making. Radheeka is a data scientist with more than 15 years of experience in analytics, causal inference, experimental design, and survey research. She has been working at Meta in California for the past 10 years and is currently leading a team of data scientists that supports the growth of Meta's advertising products. Radheeka is a proud alumnus of the University of Colombo Faculty of Science, and she holds a master's and a PhD from the University of Southern California, Los Angeles. So with great pleasure, I would now invite Dr. Radheeka Jayasundera Abeyweera to deliver the keynote speech. Over to you.
Thank you, Soumya, for this warm welcome and introduction. And thank you for the organizers for inviting me to this inaugural conference. It's so impressive to see this many women in data science from Sri Lankan origin. It's really nice to see the growth in data science in Sri Lanka. Because when I was doing my undergrad, I haven't even heard about the field. So it's nice to see that we have come a long way. So since today is the corporate session and tomorrow is going to be the academic session, I thought I'll speak a little bit about my journey into data science before I get into the main topic of causal inference. The reason being I had a slightly unconventional path to data science. And I hope I can inspire more girls and women to join the data science field, no matter what their academic background is, because it's such a open and versatile field where many fields can come together and work in collaboration. I have a slide deck which I'll start to present. Let me know, Soumya, if you can see it. Are you able to see the?
Yes, I can see it.
All right, so I thought it'll be kind of fun to talk about my journey with logos of the institutions that I was part of as a way to kind of make it less boring. So I'll start with my journey in school. So I went to Sirimao Bandanayake Vidyalaya in Colombo 7, and I went there from grade 1 to grade 13, and I graduated in 2002. And I wasn't a particularly academically gifted student. I was average. I will be in the first 15 out of a class of 50 maybe. And I also spent a lot of time outside the classroom more than inside the classroom, because I was into sports and drama and debating quite a lot. I did swimming as my main sport and water polo. And then I loved theater and drama, stage drama. So I would write scripts about different plays for English Day or, Science Day, and get people to practice and rehearse. And I also participated in debating, which was something I really loved doing. The reason I mentioned that is I think data science is a very technical field, but the soft skills are also very important to be successful. And I think the extracurricular activities are really helpful in that, because you learn to work as a team, you learn to lead a team when you do a lot of extracurricular activities, and you also learn to fail. I think as a swimmer, I probably have lost more races than I have ever won. But losing really helped me to kind of get back up and try again and again. And that kind of muscle memory is really helpful in your career, especially in data science, because you will have a lot of failures. So trying over and over again without kind of feeling down about it is really important. And I think that muscle memory is really helpful if you have it from school days. So for A-levels, I did combined maths, chemistry and physics. Back then we had local A-levels. I got a 2 Bs and a C, and not enough marks, just below the cutoff mark for the Z-score to get to Colombo University science faculty. And that's the only university I wanted to get into because they had a really good swim team and a good sports team. But back then, the University Grants Commission will kind of allocate a few vacancies for students who do curricular activities and have a small, gap for the cutoff mark. So they interviewed me and they gave me the opportunity to join Colombo University science faculty. And we started a little bit late because we are like the last people to join the batch. And in Sinhala, they used to say boat wing, because we are the last ones to join. There I decided to do, let me run my slides. P4 combination, for those who are familiar with it, it's basically applied maths, chemistry, computer science, and statistics. At the same time, I started CIM, which is Chartered Institute of Marketing. I wanted to broaden my kind of knowledge base outside pure sciences because what I was learning in university is pretty much very pure science driven. I also did a part-time job. That was mainly because I wanted to get pocket money, like to buy stuff, not so much to get an education or learn anything new. But what it helped me was I actually joined a company called Nielsen as a freelance survey taker. And they were on Duplication Road, so very close to our university. And so it was just like 5-minute walk to the office. And there I learned about data collection. So I had to go house to house, to fill out surveys about people's consumption, what toothpaste are they using or what, washing powder are they using. And some surveys were like, 50 pages long. And you also had to call people to collect data. So I learned a lot about data collection and the importance of data collection, randomization, sample representation, things that, I was learning in university, but also in practical sense, I got to learn. At the same time, I was also doing swimming because that was my main sport. Then I also, got into the basketball team and the rowing team. I wasn't that good, but I, really trained hard to get into at least to represent the university. And I also got to go to represent Sri Lanka at the World University Games in swimming in Turkey. So that was like the reason I mentioned this is these are important things I think to do while you're in university if you're still there. It's probably the only time that you kind of get to do this many things without a lot of family responsibilities. It also like really helps you mold, I think, to become the person you are as a corporate citizen. So with all that, and I also did drama. I did a small part in the arts faculty play called Poeta Puppet and a Papadam was the play, and it was really nice to be part of a big production at Lionel Brent. So with all this going on, I was really also trying to get into the special program. And back then, maybe 15 students would get into the statistics program. We didn't have multiple programs back then, and out of 300 intake. So I didn't have enough marks. I had good marks, but it wasn't enough because it's so competitive to get into statistics special program. So I ended up doing a 3-year degree. And then I started working at my uncle's company called Research Consultancy Bureau. And there I actually learned the entire research process from research question development, hypothesis development, collecting data, processing data, then analyzing it, building models, and then making recommendations, all the way to presenting to a client to convince them, what they should be doing. I think that was my kind of really initial data science kind of role, although it wasn't called a data scientist role. And that also got me interested in social science. So I've never really studied social science before because I was doing math. But I realized how much statistics and mathematics come into play when you're trying to understand human behavior, because you try to understand humans as a population, and there's some kind of consistency in their behavior. And I thought I should do further studies, a PhD in this field. because I get to use my math knowledge, but also apply it to human behavior. And I also wanted to go abroad, live independently, be financially independent and get some experience outside Sri Lanka. So I applied to mostly US universities because they kind of give funding or assistantships to help you, finish your education. I think out of the 4 universities I applied, 2 accepted me, one at University of Virginia, one at, the one I ended up going to University of Southern California. And there I got very lucky. My dissertation advisor, who eventually became my dissertation advisor, started a population center that required someone with a math background, because you had to do a lot of calculus and a lot of math manipulation with data. And that allowed me to have a research assistantship throughout my 5 years at USC, University of Southern California. And this is where also I started learning about causal inference. One of my dissertation papers was on structural equation modeling, which is, back then was kind of a new thing. I really enjoyed that, and I really wanted to kind of learn more about it. And I graduated in 2012, and it's very difficult to find jobs in academia, especially in the area that I was living, because I got married and moved to where my husband is in the Bay Area. And there, getting a faculty job is really difficult. So I ended up getting a postdoctoral post at UC Berkeley, University of California, Berkeley, in the demography department. But, as some of you know, you can't really get a permanent visa to live here legally in the US. So I had to kind of find a way to get a more permanent job. And I think I applied to at least 100 different corporate jobs, got rejected from majority of them, because back then they would ask for like SQL type of skills, which I didn't have because I've used, SAS or Stata for my dissertation, not so much, the corporate tools back then. But luckily I got this one job in a small startup called TinyCo as a data analyst. And there I learned about data manipulation, dashboarding, SQL. And it was kind of my first, real data science job with actual live data. But soon, maybe after 4 or 5 months, Facebook called me for an old application that I have put in. And they were interested in my demographic background because they were looking into audience research as an area to invest. And I obviously said yes, because that was very much aligned with my background in terms of the techniques I use, but also the area, which is demography. So I joined in 2013, that was 10 years ago, as an audience researcher. And soon I started working on products, advertising products on Facebook, Instagram, WhatsApp, Messenger. Got a lot of experience on all sorts of products and how to analyze. But most of the time, the focus was on establishing causal relationship between what we are building and what the outcome that the advertiser is looking for, because we are an advertising platform. So that's my journey. The reason I shared, like I said, is to inspire other people who don't come from a conventional background. Data science is for everybody. A lot of the people on my team actually come from economics or political science or neuroscience kind of background, which you wouldn't think that's the kind of background that you look for, but it really doesn't matter as long as you're really focused and dedicated and resilient and and interested in data and looking at relationships and understanding patterns. Then I think anyone can do data science, and I hope more women join this industry. So with that, and I'm happy to answer questions on this journey if we have time. Just checking, it's almost 10 my time. So the next, the main presentation I have is actually on causal inference for smarter decision making. So the reason why I chose this topic, because it's very close to my heart, but also I think we don't use causal inference enough in data science. It kind of tends to be a very niche skill set in most companies. But I think, it should be used more often because it's such an important concept that everyone should understand and should be using to help their companies make better decisions. So my hope is that at the end of the presentation, if even one person is interested in learning in causal inference to pursue it, then I think I've done my job. So with that, I'll kind of talk about the outline of the talk. So there's two kind of sections. I'll spend some time trying to kind of explain why causality matters with a few examples. And then we'll go to the second part of the talk about how we establish causality, like what methods that we can use. Okay, so what is causality? I think given that most of us are data scientists or have some background there, we all know that correlation and causation is not the same thing, and we shouldn't be kind of confusing the two. But in reality, I think when we build predictive models, ML models, AI models, we always we use correlation as kind of a starting point to add variables into our models. And it's okay to do that for the most part if prediction and accuracy of the prediction is the main thing that you're going for. And why certain variables impact each other is not that important for your research question or your decision, then it's okay to do that. But more often, we want to be able to understand why something impacts another thing, or what if you do this, what will happen? Like, what are the kind of what if scenarios? So in those instances, we cannot really use prediction-based models to make those inferences. You have to have proper causal inference methods to do that. So to explain a little bit further, I'll go with the most common example I've ever seen. I've seen this in many presentations, but I thought I'll start with this. So this is actually a kind of fictional graph that I made based on other things I've seen. So if you look at the northern hemisphere, and the kind of the weather patterns, the summer months are the most warm months of the year. And if you look at like variables like ice cream sales and shark attacks, you'll see almost perfect correlation between the two variables. And we know the reason why this happens is that when the sun is out, it gets warm, people like to go to the beach, and when they go to the beach and swim in the ocean, then they're more susceptible to shark attacks. And at the same time, when it gets really warm, people also like to eat ice cream, and that increases ice cream sales. But intuitively, we know that these two variables are not correlated, and we wouldn't ever put them in a ML model as a feature to predict one or the other. But this is like a classic example of why correlation is not causation, because there's a confounding factor here. The second example is actually something I took from this really great book called The Book of Why by Jude Apel and Dana McKenzie. They show how sometimes correlation without like fully understanding the why kind of lead to incorrect conclusions. And in this case, if you look at the left-hand side graph here, exercise, it seems like when exercise goes up, cholesterol also goes up. But we know from the medical literature that that's not the case. Exercise actually helps, to reduce cholesterol. And why is this happening? And I think the reason is, here in this case is age. If you cut this data by age, you see the relationship actually has reversed. And that's because, there is a confounding factor, which is age. As you get older, you might have more cholesterol, so therefore you might have the tendency to exercise. But we know it's not caused by exercising. Cholesterol is not caused by exercising. This is called, I think that, technically called heterogeneous treatment effect. It's also a very good example of Simpson's paradox. And this is another downside of just looking at correlation as a way to make decisions. In this case, the decision is, should I exercise to reduce my cholesterol level? But there are many, many examples where there's, the relationship is not what it seems to be. And if you don't thoroughly understand it and study it and understand why, you might make the wrong conclusion. The next one is a little bit a fun one and not exactly in the same lines, but if you think about how important it is to understand why, this is a very kind of a good example. So if, the question here is, if it takes 5 hours to dry a t-shirt in the sun, how long does it take to dry 4 t-shirts? So if anyone knows the answer, you can answer. If not, I can't see the chat, but I can answer for you. So as it'll be the same number of hours, right? Because the sun is a renewable resource, it is in abundance, so we don't really need to think about it as something that requires additional hours. But if you ask ChatGPT, which is like amazing in so many ways and gets most of the things right, it has passed the bar exam, medical board exam. But if you ask ChatGPT this question, and you can try this at home, they will tell you that it's actually going to take 20 hours. And why is that? Why does such a smart AI based model kind of give us that answer? And I think it comes back to the lack of understanding of why something happens. As humans, we know intuitively, common sense, we know that the sun, is a renewable resource. It's in abundance, and we, you can't think of it as like a dryer, like electric dryer. But without feeding that information into the models, you cannot really get the right answer. And you could say, okay, the model needs more data, but common sense and intuition, like just knowing things as humans, it's like a lot of information to feed. I think there is going to be a time where we won't be able to feed every data point into the model to get it right. And this is why, again, I think, we need to understand why certain things happen when we make decisions, because prediction-based models do not always give the right answer, as you can see here. And the last example, I promise you this last one, this is to make a different point. So this is actually a paper that's online. It's not published yet in journals, probably because I think this is a simulated data set. The question that these researchers are trying to answer is like, how accurate is the object detection models? These are usually used in self-driving cars, right, to detect pedestrians on the streets, like if someone is there or not. And what they found was, through some of the simulations, is that the model has 5 percentage point less accuracy in detecting dark skin pedestrians versus light skin pedestrians. And I think the reason that they were saying was the training data set that the model is using is mostly based on light skinned people. So whenever it kind of goes away outside of that training data set, the model cannot predict properly. So what does it say, about ML and AI is that, it's very hard to generalize the moment you move away from the population that you have trained the model in. And that's another kind of downside of, purely relying on prediction. And there's a new field that's coming up called causal AI that kind of tries to solve for that, the generalizability outside the population that you're studying, which is hopefully, going to be, will be used in the future in things like self-driving cars, because there's so much you can feed the model in terms of data. Okay, so those are the 4 examples I want to get through. In summary, what we talked about was the downside of using just prediction-based models for decision-making is that there's always going to be unobserved confounders, like the sun and the ice cream shark attack example, which kind of give you the wrong kind of recommendation, which is very important in your data set. And there's spurious correlations, like we talked about, the cholesterol and exercise example, and then lack of generalizability. I think, not being able to kind of move out of the bounds of the population that you're looking at really, kind of limits the value of some of the models that we are building. And the last one is actually becoming more and more important. I think in countries like in the EU, European Union, and like UK, there are new laws kind of mandating companies to kind of disclose information that kind of is based on ML or neural network kind of model. So for example, if say, you apply for a loan application and the ML model kind of rejects you from the loan application for whatever reason, the law now kind of dictates that you have to explain to the person why it was rejected. Was it because of the income or gender or age, or what is it? But if you are relying on like a black box approach, like deep learning or neural network based model, I think you cannot really explain why someone got rejected. So that kind of really prevents, the companies from using them in their production level models. So that's another challenge that we are facing with, just, using prediction alone as a way to, make decisions and kind of, put people in different buckets. So given that, if it's not even, that obvious, but I wanted to kind of highlight, like, what is the downside of, like not using cause and effect based thinking or decision making. I think the most important one, because this is the forum of industry or corporate data scientists, I think is the financial risk, right? Anytime a company makes an investment, there's always this what if question, right? What if we spend on this versus that? And kind of having more scientific answers of what the outcome would be will help the company save money. And this is very evident in advertising, because advertising is a very expensive investment. But if you kind of don't really know the best way to do it, or just, try things out without scientifically measuring it, you're not really using the investment in the best way. So I think that's a main kind of thing for the industry's financial loss is the main kind of risk. In the healthcare sector, I think this is sometimes life and death, right? We really need to understand why a certain drug works better or certain medicine works better for certain illnesses, or does a vaccine really work? Like during COVID, I think we learned a lot about RCTs or randomized control trials, where you put people into two groups to test out a vaccine, and that's to get the answer absolutely right, because you cannot take a risk when it comes to people's healthcare. And the last one is policy, mostly government policies, and some of them are health related also, like things like education or employment. All of that can have significant impact on the population that who are subject to those new policies and laws. So governments have to get these things right for the most part, right? And experimentation and causal inference, I think, comes to play there, because the risk of not getting it right is huge. So this is why causal inference is important, and this is why I hope folks who are in the audience, if you haven't kind of delved into that, will feel a little bit enthusiastic and encouraged to look at causal inference in your day-to-day job, so that you can help your company or your employer make better decisions. All right, so that's the first part of the presentation or the talk, because I kind of wanted to establish why it's important. So now we're going to move to like how we do this. How we do this in the corporate sector, especially, but also outside corporate, like in government or in policy settings as well. I will go through. I will use one example as much as I can, so there's some continuity there. So if you kind of really simplify the question of causality, it's about establishing cause and effect, but also answering questions like, what if we do this? Like, what is the counterfactual? If we do this and not that, like, what would be the outcome? So just to simplify, and I'm really simplifying it here, it's basically, taking this example, if you run this advertising campaign, which might cost millions of rupees or millions of dollars, will my sales go up? Let's say we are launching a new product or launching a new service, and you want to know whether the sales or the adoption of the product goes up or down through advertising. And that's like a very simple question. I think if you just kind of present it that way. But the challenge to kind of answering this question is that, and there are many challenges, but the one that I'm going to focus on is on confounders, is the other variables that could impact both outcomes, right? So going back to the example of advertising, if you are running an advertisement during Single and Tamil New Year, then you might see sales going up regardless of the ad, because people are buying food, buying gifts for their loved ones. So we cannot really establish whether the advertisement really helped the sales growth or not. Similarly, if there was a tax concession, I know tax is a big topic in Sri Lanka. Let's say the government decides to reduce tax for essential goods. They remove the VAT for, let's say, for certain like food items. Then you might see, the sales going up regardless of the advertisement. So how do we kind of tease that out? And same thing with pricing. Like, if you're going to reduce the price, or buy one, buy two, and buy one and get two, like some kind of promotion like that, that could also increase sales. But then, did it really matter whether you ran an ad or not? So these decisions are really important because the investment is huge. Like I said, the financial investment, and similarly, it could be other risks like health and government policy. So for the most part, this is kind of what I'm going to talk about in terms of the solution, but there are other issues and other frameworks to think about. So causality can be kind of compromised by having mediators. Sometimes you might have reverse causality or cyclical. And then there's also the domino effects from one thing, impacting another. And there are much more sophisticated ways to address them. And then this kind of approach on kind of, reducing the impact of confounder is one way. Another way is using structural equation model, which is something that I used for my dissertation back in the day. And then also looking at potential outcomes. So, but here I'm just going to focus on how we kind of handle confounders as a way to explain how we do causal inference in the industry and in the corporate sector. All right. So the gold standard, or the best method for establishing causality is experiment, or A/B test, or the fancy word is randomized controlled trial, or RCT. All means the same thing. And what we try to do here is we try to kind of reduce all the confounders or all the other factors that could impact the outcome that we are looking at. And the way we do that is we take a group of people and then break them into, two similar groups. And that, when I say similar, it should be, based on age, gender, education, income, location, health status, and all of that. And also they should be exposed to the same environmental factors, like same weather, same, macroeconomic crisis, or same unemployment, same kind of environment that compared to the group that's going to have the treatment. So once we have the randomized to the two groups, only one group gets the treatment or the intervention that we are going to test out in our analysis. So again, going back to the advertising and sales example, so keeping the same example throughout the presentation, we will take the treatment group, we will apply the advertising, or will expose this treatment group to the advertising campaign. The very similar group does not get exposed to the advertising campaign, which is the control group. And then we run this kind of experiment for maybe a couple of weeks or months, depending on how big a sample we need to detect the impact. And then you compare the sales of the exposed group versus the sales of the non-exposed group. And that's what we call treatment effect. It's very simple in terms of the concept. I think execution is quite hard, but this is the most pure form of establishing causality between two variables, cause and effect, because you control for everything possible and the things that you can see and also you cannot see for the most part. So like I said, it comes with a lot of drawbacks, but I think, and also there was also this thinking like, experiments are only in like, pharmaceuticals, like, you can only do it in a pharmaceutical environment because it's really hard to manage. But in 2019, the Nobel Prize for Economics actually went to 3 economists, Abhijit Banerjee, Esther Duflo, and Michael Kramer, for their experimental work on very precisely answering questions in education and healthcare in developing economies. They did a lot of like experiments in India and a few other countries where they really, did the randomization and control for a lot of things. And I think it's one of the, starting points, at least in the development economics area, to start thinking about using experiment as a tool to understand policies and the impact of policies on human population. I'm going to go a little bit quickly because I only have 10 minutes. The downside or the challenge with experiment, there's a lot of challenges that prevents us from using for every use case, is that it can be unethical. Right. So if you think about, back in the day when we're trying to establish smoking and lung cancer, you cannot ask 2 groups of people, one group to say you smoke every day and the other group to say not smoke, right? That's not ethical to do. And there are many, many instances where you cannot, the treatment is not ethical to apply in that way. So you cannot use an experiment to understand the cause and effect between those variables. The second reason I think is, the expenditure, like the cost of running an experiment can be quite hard. Quite high because you have to recruit participants, you have to incentivize them sometimes, you have to have people running the program, you have to hire people to do it. So sometimes it's really like prohibitively expensive to do experiments. The third reason is it's time consuming, takes many months and maybe years to plan something out. And sometimes people, fall out of the experiment, they do their own thing, they don't follow the instructions, so they need to recruit more participants to the experiment. So it just becomes really hard to do it, especially in a policy environment. It's not that hard, I think, in my field at least, when we're thinking about digital advertising, but still, can be expensive as well. And the last reason is, if you're looking for something that's in the long-term horizon, then we run into network effects, meaning that the people in the treatment group might influence the people in the control group. So there's contamination and the experiment doesn't work. And I think for long-term treatments, it happens a lot, which makes it really hard, for us to do experiments. And there are many, many reasons why experiments might not work. So then what do you do? When you can't run an experiment, but you have to establish the cause and effect, what do you do? So in the past, I think maybe in the 80s, I read about it, like, an economist tried to establish causality without experimental data. They didn't quite get it right. And, for a while, there was kind of a little bit of a negative perception over non-experimental based causal inference. But thankfully, we'll talk about later, there was some pioneering work done by three other economists who eventually won the Nobel Prize in 2021 that really showed that non-experimental methods can get very close to actual experiment outcome. So how does it really happen? So I think the best way to explain it is to go back to our early example, which is looking at advertising and non-advertising, groups, and then looking at the treatment effect. In a non-experimental environment, what we run into is the bias, and the bias can come from the mediating variables or confounders or whatever that is not something we can control for in the existing data. And our, kind of attempt is to reduce the bias and make it, close to zero as possible, so that the comparison is clean as possible, so that the treatment effect is accurate. And there are many methods to do that, which we'll talk about. But just really quickly going back to what I mentioned earlier, these three economists and one other economist, which I forget the name, who passed away before the Nobel Prize was given to them, really pioneered natural experiments, an instrumental variable approach that kind of reduced that bias that I talk about to almost zero, so that you can get to the most accurate answer as possible. So if you get a chance, read about their work. It's quite interesting. It's in labor markets and labor economics, but it's still relevant to corporate sector and in the industry. I think the methods they used is quite applicable. Okay, so given that I have 7 minutes, I'm going to try to go really fast. So in terms of causal inference method, there's a lot of methods that are coming up as we speak. I got trained 10 years ago, and what I learned is so outdated now. There's many more modern methods and conventional methods that do a really good job of getting close to an experiment than what I've used in the past. Actually, my team keeps me up to date because what I've learned before is like quite prehistoric, if I say so myself. So what I'm going to do now is just explain two simple methods just to help you understand the concept of non-experimental methods. The two that I'm going to explain are not the best methods, right? There are much more sophisticated methods that are out there, but that requires a little bit more understanding of causality and how the models work before you use them. So just for simplicity, we'll talk about matching methods and difference in difference if you have time. And then we'll talk about how we check for validation, which is a very important step. And I do not recommend skipping this step if you're going to use causal inference models. So matching methods, the basic concept, I'm really simplifying it here, is you basically take a group of people who are already exposed to a treatment. So in this case, let's say advertising, they're already seeing the ads and you didn't have, for whatever reason, you couldn't have a control group. And what you try to do in a matching method is to find a match for each individual, or almost like a twin for each individual using propensity score matching or some other kind of technique to understand how similar is this person to the other person who didn't get exposed. And you do that, for every person in the treatment group. And sometimes you might have more than, one match for each person, increase the strength of the analysis. But basically, you try to kind of create an artificial A/B test post the treatment. The challenge with this method is that you can only match on things that you can observe, like age, gender, income, maybe behavior. But if there's something that inherent to the person, let's say a health issue that we don't have data about, and that's very important for the outcome that you're looking at, you cannot match on that. So not being able to match on every possible variable sometimes causes this method not work. But there are times that it might work. And so it's worth trying, but it's also good to try other methods that are more sophisticated. The second method is difference in difference, which is a little bit easy to understand as well. Here we are trying to look at like a certain treatment that happens in a certain kind of environment. So I kind of came up with a Sri Lankan district, Gampaha. Let's say there's an advertising campaign that happened in that district, and we want to see how sales have increased over time. If we just do a pre-post analysis before the ad and after the ad, there are a lot of issues with it, because there could be something that caused the sales to go up outside advertising. And we talked about, maybe a holiday that is very unique to Gampaha, or a certain tax concession that is very unique to that city or that district, or certain weather situation that is unique to that district might increase the sales regardless of ads. And in this situation, we might be able to find a similar district that has similar kind of trend This is what we call parallel trend assumption. Basically, you will need to find a similar geography. It doesn't always have to be a geography. It could be a cohort of people that has a similar trend over time, and you assume that the cohort that is being exposed to the treatment would have had the same parallel path if there was no treatment given. In this case, if there was no advertising, and that's what this dotted line is showing. And the effect of the ad is, in this case, would be the difference between this and this, and basically this small part. Again, this method comes with a lot of challenges as well, but it has worked. And the three economists who won the Nobel Prize for 2021 actually used this method quite successfully. This was to look at minimum wage change. So like in the US, there's a minimum wage that you have to pay to low-skilled employees. And there was a change that was done in one state, in New Jersey, and they wanted to see if that impacted unemployment in any way. And they used Pennsylvania, which is a similar state, as a kind of comparison to do the estimate. So this method has its merits, but also comes with drawbacks, because you have to have the parallel lines, and you also have to make sure the intervention does not impact, is not influenced by the outcome. But hopefully these two methods are kind of gives you an idea of what causal inference is, and there are like many more methods, like I said, which are much more accurate. But whatever I think we end up doing, I think it's very important to understand how we validate these methods. And the best way to do it is to actually compare multiple methods and see how each model performs. Another way to kind of look at how valid your model is the effect size. So I think in the smoking and lung cancer example back then, it was, a lot of people challenged it, right? The tobacco companies challenged whether actually smoking is causing lung cancer. And I think one of the ways they defended it is like the effect size of smoking was so high that no other variable can really explain that variance. So if your effect size is very large and your confidence interval is narrow, and your models are giving the same answer in terms of the estimate, but also the direction, I think it's a good sign that your model is establishing the causality, or is getting close to causality. And there are also other methods to like sensitivity analysis or robustness check by adding noise, replacing certain variables and adding noise to see if the model will give the same answer. So there are more methods. I'm quickly going through them. The last thing I want to leave you with are the books and the videos that will help you to learn more about this field. Like I said, this presentation is not going to give you the ability to go and do this analysis. You'll have to like invest time, and I hope you do. And there are also a lot of free materials on YouTube. I think Coursera, I think you probably have to, some of the courses you have to pay, but there are a lot of free material out there about causal AI and causality in general, which gives you a good overview of how to use these methods to make better decisions on behalf of your company, so that you can save more money for the company, and also, maybe make, better decisions on behalf of the consumers as well. So that's my presentation. I'm 1 minute over, but hopefully that's okay, Soumya.
Yeah, that's totally fine. Thank you very much, Dr. Radheeka, for enlightening us with that very informative speech. So now I'll open the floor for questions. So if you want to ask questions from Radheeka, you can use the Zoom raise hand option, and the meeting host will unmute you. Any questions for the speaker? Seems like we don't have any questions. So thank you once again, Radheeka, for enlightening us with that very informative speech.
Thank you. You're welcome.
Yes. So moving on. So next, get ready for an electrifying session as we dive into our next agenda item, the lightning talks. So in this high energy segment, we have not one